In this video, we begin our detailed look at infinite series. Now, just as a reminder, let's give an overview of how infinite series tends to be analyzed, right? So suppose we have this infinite series, k going from 1 to infinity. So here I'm assuming that my index starts at k equals 1. And remember, all that an infinite series is an infinite sum, right? So we're adding up infinitely many terms, and that's not something that we can physically do. So what we do is we're going to end up using a limit to help us simulate this infinite sum. And what we do is we define our nth partial sum, right? And that's the sum of the first n terms. And for the sum of the first n terms, my index would have to go from k equals 1 to k equals n. And then we would end up with this finite sum. Now this is something we can do, right? This is something we can actually do. We can add up a finite number of terms, right? The big thing is, though, how simplified can this be, right? And that will be our objective for some of our special infinite series. But once we have this expression, we then ask ourselves, what is the limit as n goes to infinity of this partial sum, right? And then, so we look at this limit to see if the limit exists or not. And if this limit exists, then we say that our series converges to whatever number that limiting value is. And if this limit does not exist, then we say our series diverges, right? So the process of finding this nth partial sum in general is a difficult process. You might say, well, how difficult can addition be? Well, it depends on the complexity of the terms that you're adding up, right? Well, for a few special series, the process of finding S sub n is actually fairly straightforward. And one of those series is, in fact, what we call a geometric series. So what we're going to do is give the definition of a geometric series, figure out a way to find its nth partial sum, and then see what happens when we take the limit of that. See if we can get any nice results, any theory that will enable us to analyze these series quite effectively. All right, so let's go ahead and do that. So first, we need to know what a geometric series is. So a geometric series is any series of the form, right? And let me write down the sigma form first. So it's the sum, and here I'm going to choose to start my index at k equals 0, right? And then go to infinity, and then it's anything of this form, a times r to the k, right? Where a is a constant, r is a constant, so my exponent here is what changes, right? So if I were to write, so we can see the first few terms of this infinite series, it would be like this. It would be a times r to the 0 plus a times r to the 1 plus a times r squared plus a times r cubed, and so on indefinitely. I put my ellipses there. Well, r to the 0 is 1, right? And a times 1 is a. And then here we can drop the exponent of 1, so we have a times r, and then a times r squared, a times r cubed, right? So that's a geometric series, and you can see the pattern. It's like you start with a number, and then you successively multiply by another number r, right? So you start with this first term, and we multiply by r, and we get the second term. And we multiply by r again, and we get the third term. We multiply by r again, we get the fourth term. So it's this successive multiplication by r that generates the subsequent terms, and for it to be a series, we have to add them all together, right? The number a, right? So a, which is some real number, right, is called the first term. Man, how did we ever come up with that description, right? So it's called the first term of the geometric series. Right? And R has a special name as well, but before I give you the name, let me kind of give you a motivation for where the name comes from. So let's say, in fact, let me write out a few more terms. So for instance, the nth term of this series would be a times r to the n minus 1 because my counter is starting at 0, right? So it's 0. This is the first term, this is the second, this is the third. So whatever the exponent is, if I subtract 1, then it will tell me what place or let me put it this way. If I add 1 to the exponent, that will tell me what place or what term that term is in the series. So this term is actually the fourth term. This term is the third term. This would be the nth term. And then let me write the term that would come after this. So then this would be a times r to the n, right? And then it will continue, right? So let's take these two consecutive terms, right? So the two consecutive terms anywhere in the series must be of this form, right? So any pair of consecutive terms must be of this form, right? So it must be of the form ar to the n minus 1, and then the next one would be ar to the n. Now if I wanted to, I could do ar to the n, and then the next one would be ar to the n plus 1. So whichever one of these I wanted, whichever pair I wanted to take, then it would work, right? So let me take my original pair, and let's take the ratio of these two numbers. So let's take the subsequent one divided by the previous one, right? You may say, well, why am I doing that, right? Well, let's see. So the ratio of any pair of consecutive terms terms is this. So let's take the ar to the n and then divide it by ar to the n minus 1. Well, how does this simplify? Well, they have a common factor of a, right? So the a's go away, and so I have r to the n divided by r to the n minus 1. But a property of exponent says whenever my base is the same, in this case it's r, and I'm dividing these expressions, I have to take the difference in the exponent. So this will be r to the n minus the quantity n minus 1. Well, if I look closely at this exponent, I have, if I distribute this negative 1, I'll have n minus n and then plus 1. So I end up with r to the 0 plus 1, so that gives me r. Right? So what this is saying is, if I take the ratio of any pair of consecutive terms in a geometric series, I am always going to get this constant. See, regardless of what n is, if I take the ratio of these consecutive numbers, then I will always get this constant. And for that reason, right, r is called the common ratio of the geometric series. So the number r is called the common ratio, right? Because it's the ratio of any pair of consecutive terms, right, of the geometric series. right? So we have the first term, that's our number a, and then we have our common ratio, that's our number r, right? And these two are very significant in terms of analyzing geometric series and coming up with the nth partial sum and what's going to happen when we take the limit, right? Well, speaking of that nth partial sum, let's take a closer look, right? So S sub n will be the sum, and remember, we're starting at k equals 0. We could easily do it as starting with k equals 1. The algebra will amount to pretty much be the same. But now we're going up to n minus 1 because we want the sum of the first n terms. Remember, that's what S sub n represents, right? It's the sum of the first n terms of the series, whether it's geometric or not, right? Every series we define this nth partial sum as the sum of the first n terms. So since I want only the first n terms, my counter starts at k equals 0, then it has to stop at n minus 1. And then again, remember our pattern is this. So let's write it out. In fact, it's kind of what we had there or above, except we don't have the dot 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 because we're stopping the sum, right, at a particular point. So it's a plus ar plus a r squared plus, and then dot dot dot, and then plus ar, and then the very last. In fact, let me write the second to last term. So this is the penultimate term in our nth partial sum, and then this will be the, I guess, the ultimate term or the final term. So like that, right? So this is the expression for S sub n. So let's rewrite it down here, and then let's just play around with it, do some algebra, see what we can come up with. So, you know, the question is, like, again, because the number of terms is kind of arbitrary, it's not fixed. Like, we know it's finite, but we don't know what n is. Is it 2? Is it 2,000? Is it 2 million? We don't really know. So it makes it hard for us to think of, you know, like, how could we possibly simplify something like this when we don't even know the specific number of terms in the expression? The only thing we know is that it's a finite number of terms. Well, there's a really standard trick for geometric series, and this is what we do. We're going to take that common ratio, and we're going to multiply both sides of this equation, right? So I'm going to call this first equation equation 1, and then I'm going to look at r times S sub n. And what I'm going to do is, like, I'm going to shift it over. Instead of starting to write it right below, I'm going to write, so if I multiply this term, it becomes AR, right? And I notice there's an AR there, so I'm just going to put it right there, right? So I kind of shift it over a little bit. Then if I multiply the second term, this becomes AR squared. And look, there's an AR squared, so I'm going to put that here. And then the same thing will happen when I multiply this. I'll have an AR cubed. It would have gone here, but this is where I'm going to put the dot dot dot. Now, the term previous to this one, right, would be AR to the n minus 3. But when I multiply AR to the n minus 3 times r, again, I would have to add 1 to the exponent. So the term that comes before this one, when I multiply it by r, it will get shifted here. So I'll have the same term here. Similarly, when I multiply this term by r, again, I would add the exponents, and then I would get this term, so AR to the n minus 1. And finally, when now that I look at it, this might be misleading. Let me take these off and just say this is equation 1. I don't want the dot dot dots for you to think that it goes on forever. This is just the label that I'm using. Finally, if I multiply this term by r, again, adding 1 to this exponent gives me a times r to the n, right? So we essentially have two versions of the same equation. This is the nth partial sum, and this is the nth partial sum times that common ratio. But they have so much in common. Look, they have all of these in common, right? So if I call my bottom equation now equation 2, if I were to take equation 2 and subtract equation 1, that everything that I have highlighted in red here or boxed in red, right, would cancel out, right? So the dot dot dots, even though again I don't know how many are there, I know that they're identical. They show up in both equations. So if I take my second equation and subtract my first equation, this is what I get. On the left-hand side, I would have rs sub n minus s sub n. Then I'd have my equal sign. I'd have 0 minus a, right? So I'd have like a negative a. Actually, yeah, we could do that. So we'll have a negative a. And then I will have all of these in the bottom equation minus the exact same thing, the exact same terms in the top equation. So those would all cancel out. And then I would have this term minus 0 because this term isn't in the first equation. So I'd have this last term still left there. All right. Okay, so we have this, right? And then if so I can rewrite this. So I have r times Sn minus Sn. I can write this now as a r to the n minus a. And then look, on this side, I can actually factor out s sub n because it's a common factor. So s sub n, and then in parentheses I have r minus 1. Over here I can factor out an a, and then in parentheses I'll have r to the n minus 1. And then I can divide both sides by r minus 1, that quantity. So therefore, here's a formula for my nth partial sum. It's this quantity, a times r to the n minus 1, divided by r minus 1. Now, so it can be written like this, but I'm going to multiply the top and the bottom by negative 1 because I want to have the 1's first. So if I multiply the bottom by negative 1, it becomes 1 minus r. If I multiply the top by negative 1, I'll still have an a, but then I'll have 1 minus r to the n. Right? So it's a little bit easier to see what happens here. So this is a formula. So we actually have a formula now for the nth partial sum of a geometric series where the first term is a and the common ratio is r, right? And this in itself is a useful formula. It's a useful formula when you're summing up a finite set of terms that are in what we call geometric progression. You might actually remember that phrase from your work in algebra, right? So this in itself is a useful formula, but this is not our end goal. Our goal now is to ask what happens to this expression as n goes to infinity, right? So now we have to figure out, so what happens to s sub n as n goes to infinity, right? Well, what makes this not so difficult is that there is only one term in this entire fraction that has an n there, right? So we can focus on this and say, well, what's going to happen to r to the n as n gets very large, right? We can focus on that because all the other terms are constant. They're not affected by n, right? So let's see. So we can translate this. We can kind of simplify this question to say, what happens to r to the n as n goes to infinity? Well, it depends on r. And remember, r at this point technically can be any real number. Well, let's see. Let's see what are some of the possibilities. If r is bigger than 1, so something like 2.5 or 10 or 25, then at r to the n will also go to infinity, right? So if r is bigger than 1, then r to the n goes to infinity as n goes to infinity. Yeah, this is as. It doesn't look like as, but yeah, right? So that means in this case it would diverge, right? Because the numerator would just get really, really large. So this means that s sub n would diverge. So no good, right? Okay. Now, if r is equal to 1, we also have a problem, right? Because look, in the denominator, right, we would have a 0. We can't have that, right? So if r is equal to 1, then the s sub n is undefined, right? So s sub n is undefined. So again, that doesn't work. Now, what I'm going to do, I'm going to skip down and then go to -1 and see what happens, right? So if r is equal to -1, so what would happen to -1 as n gets really, really large? Well, if you have -1 and you raise it to any integer power, then it's either going to be +1 or -1. So r to the n is going to oscillate, right? So this oscillates between plus or minus 1, right? If n is an even number, then r to the n will be +1. If n is an odd number, then r to the n will be -1 in this case, right? So again, it oscillates, so again, it's going to diverge, right? So it doesn't go off to infinity, but as we saw previously, even oscillations is an example of divergence, right? And then what if your r is less than -1? So if r is less than -1, then r to the n, again, it's going to oscillate, but it's going to oscillate between plus or minus infinity, right? Because you have a big, a relative, like you'd have a negative number, but then you're either raising it to something that's even or odd. So again, it could either be plus or minus, but as n goes to infinity, then this number will now oscillate between plus or minus infinity. So this one oscillates between plus or minus infinity. Again, diverges. So far we're running into all these possibilities where our s sub n doesn't work, right? We can't take the limit of it, right? But if you notice, I left out numbers between -1 and 1. So that's going to be our last look. So if our r is like this, right? So if we have essentially, and what this would be the set of all proper fractions, right? So any number that's strictly between plus or minus 1 has to be a proper fraction. So we're now looking at proper fractions. You know, like 1/2, -1/10, 2/7, etc. So the question is, what's going to happen to these numbers now, right? As n gets very, very large, right? Well, think about it. If you have a number where the yeah, if you have a fraction where the numerator is strictly less than the denominator, which will be all of these cases, right? Then as n gets very, very small, as n gets very, very large, each of these fractions would get very, very small. Like if you start with 1/2 and you square it, you're going to get 1/4. If you cube it, you're going to have 1/8. If you raise it to the 4th power, you're going to have 1/16. And that's the same for all of these proper fractions. So in this case, if your r is strictly between plus or minus 1, r to the n is going to approach 0 as n goes to infinity. So finally, we found the case in which our geometric series, or the nth partial sum of our geometric series, is going to converge as n gets very, very large. All right. So, well, what does that mean? So let's write down what we have for our s sub n. Remember, that was the a times 1 minus the quantity 1 minus r to the n over 1 minus r. And what we're saying now is, if r is strictly between plus or minus 1, then this thing will converge. And we know what r to the n is going to converge to. It's going to converge to 0. So if our r is strictly between plus or minus 1, then the limit of this thing now, so the limit of our nth partial sum is equal to the limit of this a times 1 minus r to the n over 1 minus r. Well, we just argued that this has to converge to 0. So this ends up being, this converges to 0. Let me highlight this. So this one approaches 0. So the entire expression approaches a times 1 minus 0 over 1 minus r, which is a over 1 minus r. Wow, so we get this really simple formula for what our geometric series will converge to, provided our common ratio is between plus or minus 1. Right? So that smells like a theorem to me. So let's go ahead and state this theorem, and this is a theorem specific for geometric series. All right? And it says this. The series, again, and this is our standard geometric series, k going from 0 to infinity, and then we have a times r to the k. This series converges if and only if my common ratio, right, that ratio of successive terms, is strictly between plus or minus 1. So if and only if our r is strictly between plus or minus 1. Additionally, right, so not only is this an easy thing to check, additionally, if this is satisfied, then we know what it converges to. So we know the actual sum of this geometric series. So this series, so then that series converges to a over 1 minus r. Right? Very simple check, very simple formula. In fact, this is the only infinite series that we will look at for which a specific formula is known, right? As far as what it sums to, right? And that's why we tend to start with the geometric series, Because yes, after going through a bit of algebra and then doing a couple limit considerations, we end up with a very simple check and a very simple formula, provided it passes this particular check. All right, so let's just do a couple examples to wrap up our video. Right. And what I'm just going to write down a couple geometric series, and then we will apply this theorem to say when it converges, and if it does converge, what is it going to converge to, right? So let's take a look at something like this one. So k going from 0 to infinity, and suppose we have like 3 times 1/2 to the k. Now, what I like to do with the geometric series, again, because they're relatively simple, it's a good idea to get into the habit of writing out the first few terms in this infinite sum, right? So you can actually see the numbers that you're adding together. Sometimes when you have the sigma notation, as convenient as it is, you lose sight of the fact that, hey, this is actually a sum, and we're actually adding up numbers. So let's write out like the first 3 or 4 terms. So when k is equal to 0, we will have 3 times 1/2 to the 0 plus 3 times 1/2 to the first power. So that's when k is equal to 1, our next integer. When k is equal to 2, we'll have that. And then, yeah, I'll just write one more. When k is equal to 3, we will have that term, and then ... So again, I'm going to put that there because, again, this is the full series, right? So if we simplify this, this is what we have. We'll have 3 halves. Well, sorry, actually that's not 3 halves. That's just 3. Come on. So we have 3. The next term is 3 halves. And the next term is 3/4, and then the next term is 3/8, and so on, right? So when you see this, you can see the first term. You can see that the first term here is 3, and then you can see that common ratio. The number that I am successively multiplying by is 1/2, because 3 times 1/2 is 3 halves. 3 halves times a half is 3/4. 3/4 times a half is 3/8, and so on. So just sometimes it's a lot easier, right? To list the terms, right, in the sum, and then you can identify. So from this, we can conclude that a is equal to 3. That's our first term, and our r is 1/2. Now, we could have seen that here, but as we will see in another example in a second, sometimes a series isn't always written in this nice standard form. Sometimes the k might not be, the initial k is not 0, and sometimes it's not just written to where you can see your a times your r to the kth power. And sometimes you might have a more complicated expression here, but that's where properties of exponents will come in. But in this case, we've identified our 2 important values for our geometric series, and then we can say this. Since our common ratio is between plus or minus 1, right, we have our nice proper fraction here, then the series must converge, right? So the series converges. And not only does it converge, right, we can say, and it converges to what? What does it add up to, right? So, and it converges to, the series converges to, so I'm going to write down the original thing, right? So here is our original series. It's geometric. We now know that it converges, and then we use that formula, that a over 1 minus r. So here is the a. So it converges to or a, which is 3 over 1 minus r, so 1 minus 1/2. So this is 3 divided by 1/2, which is 6. Right? So what this means is, if you start with 3, and then you add 1.5, and then you add, your 0.75, and so if you keep adding these terms, that sum will get closer and closer and closer to 6, right? And the more terms I add, the closer I will get. And I can get as close as I want by adding sufficiently many terms together, right? So that's our first look, right? Now, there are other ones, like I said, that can be a little bit more complicated. Let's take a look at this one. So let's say k goes from, again, 0 to infinity. Actually, let's start this one at 1, just for kicks, right? And then we have 9 to the negative k plus 2 times 4 to the k plus 1, right? So you can see this one is certainly not in that standard form for several reasons. For one, it's now starting with a value of k equals 1 as opposed to 0. And then here, like both of these terms have k's in the exponent, right? So we can't just look at this and say what r is. What we have to do, and this is what I encourage students to do initially, is to take this expression, use properties of exponents, and rewrite it in such a way so that it looks, right, more like this, right? So let's see how we would do. I'll do some algebra right below here. So let's start with the 9 to the negative k plus 2 times 4 to the k plus 1. So the first thing I'm going to do is I'm going to factor each of these exponential expressions. So the first one factors as 9 to the negative k times 9 squared. And then the second one factors as 4 to the k times 4 to the first power. Right? So there, everything is now sort of factored, and I can start to see which term or which factors are constant, and then which ones have the k in them. All right? The constant ones, let's move those to the front. Right? So I'll have 4 times and then 9 squared. That's 81. All right? Then what about this 9 to the negative k? Well, 9 to the negative k can be written as 1 over 9 to the k, and then I have times 4 to the k. So, as far as the constant, 4 times 81, well, that is 324 times, and then the 4 to the k over 9 to the k is the same as 4 over 9 to the k. All right? So this expression that we started with that didn't look like a number times a number raised to the kth power, in fact, can be written in that form. So what we've just shown using properties of exponents is that this sum, going from 1 to infinity, of 9 to the negative k plus 2 times 4 to the k plus 1, that's exactly the same as this sum, 324 times 4 over 9 to the kth power, right? But then this looks a lot like our definition. The only difference is I can't look at this number and say, oh, here's my a, because the initial value of my index is not 0. And this is where it's helpful to write out those first terms, right? So if I now write this in the kind of the expanded form, when k is equal to 1, I'll have 324 times 4 over 9. And then the next term will be 324 times 4 over 9 squared. And then plus 324 times 4 over 9 cubed, and so on. So this is actually my first term. So A is actually this quantity, which is equal to, this is 144, right? So let's write that down. So this is 144 plus, and again, all the other ones I'll just kind of leave in that fraction form, but this is the other key thing that we need in order to apply our result, right? So we have, I'll just write down the other couple terms, right, and so on, right? So I can look at this, and I can definitely see that my R is 4/9, because if I multiply this by 4/9, then I'll get this. If I multiply this by 4/9, I'll get this, right? So I can say that this one is geometric. My first term is 144, and my R is 4/9. And because my R, again, is a proper fraction, so since R is between plus or minus 1, the series converges to, and then I can use my nice formula, A over 1 minus R. So our A over 1 minus R is the 144 over 1 minus 4/9. So that is 144 over 5/9. So that's 144 times 9. That's 1,296, and then that's all over 5, right? So again, for this particular geometric series, if I continue to add these terms that are in that geometric progression, I'm going to get a number that's getting closer and closer to 1,296 over 5. And I can get it as close as I want by adding sufficiently many terms. If, however, if I stop the process, so if my addition is then a finite sum, then the best I can say is that finite sum is approximately equal to this. It will never be exactly equal to this, because again, I'll have to continue that addition process infinitely many times, right? But if I stop it at any point, I will get a number that's pretty close, or very, very close to 1,296, right? So for our geometric series, again, the highlights is 1, making sure that we can identify what a geometric series is, know the condition for convergence, and know the formula that tells us what a convergent geometric series converges to. All right, I'll see you in the next video.